For the first talk, we have Dr. Waseem Abbas here. Some of you are already familiar with him. He did his PhD from Georgia Tech University. He works in the area of control networks, and more recently, he's working in the Resilient Consensus over networks, robotics में उसकी जो application है वो, and of course in machine learning as well. He was associated with Information Technology University EE department as well for about a year or so. And currently he is at Vanderbilt University. Is a research assistant professor doing great work, and he's a really good friend of mine. And so I sort of kind of insisted him to do the first talk on this amazing topic of resilient distributed optimization, iska consensus interference network. So over to Waseem. You can start whenever you are ready.
Thank you very much, Dr. Mudassir. First of all, thank you everyone who is here right now. It's really a great feeling to be talking to the former colleagues as well as to students. So, I mean, I look forward to this interaction. So with this, and special thanks to Dr. Mudassir again for making sure that I'm awake at midnight here. So, but thank you. So today I'm going to basically talk about some of our recent work related to resilient distributed optimization. And in fact, more particularly, there is one key step in almost every distributed optimization scheme, which is resilient aggregation, how the agents aggregate other agents' data. So the talk will be focusing more on that particular aspect, which is how can we do it in a more resilient manner. So this is basically a joint work with a student, a PhD student here, Gianni Lee, Dr. Mudassir. He has been very actively collaborating with us here, and Professor Xenophon Koutsoukos at Vanderbilt. Again, I will be presenting a subset of results that appeared in these papers. Of course, it's just as, I mean, I'm picking some of the relevant results which are more suitable here. Okay, so what this talk is all about. Let me just give a very, very brief, high-level overview. And again, I'm going to repeat this again as we build up to the main topic. So what is the setup? The setup is that we have a bunch of agents. These agents are decision-making entities. You can consider them as robots, which are moving, and they have to decide which position they have to take. And these agents are interacting with each other, and basically they are cooperating with each other, and they are exchanging their information with each other. And why they are doing so? Because they are all working towards a common objective, whatever that objective is. Now, a key step here is that agents are interacting with each other and exchanging their information with each other. So, and as a result, each agent is going to basically somehow aggregate its neighbor's data and then utilize this aggregated information in updating its own state or in updating its own action. But somehow what happens along the way is that some of the agents become faulty or they are attacked. So what happens then? Since agents are interacting with each other, then this faulty information can be transferred to agents. And when during the aggregation step, nodes can incorporate this faulty or incorrect information. And why will they do so? Because the agents don't know who's the adversary. So they cannot just cipher out the bad information from their collected information. And as a result, what would happen is that when agents are going to incorporate this faulty or incorrect information during their aggregation step, then they will take the wrong action, and this wrong action will ultimately lead us to an extreme deterioration in the overall performance of the network. So what is our goal? Our goal is that we want to perform this resilient aggregation, meaning that we want to aggregate each normal agent wants to aggregate its neighbors' data, even if some of the neighbors are faulty. So we want to somehow develop a scheme where this incorrect information is siphoned out during that aggregation step. So this is kind of a more very high level overview, not very concrete, but we will make it much concrete in a minute. Just to give you an example of, okay, sorry. There is a lot of noise, so let me just mute these videos. So what is happening here is, let me just give you some of the examples of this distributed decision making setup. I mean, this is not just an abstract setup; it's very practical. And let me give you some examples in multi-robot systems. So, for instance, if you look at this first picture over here, what is happening is that these robots are trying to cover some area. Okay, and they are trying to do it in a completely distributed manner. By that I mean that agents don't know, or these robots don't know where they should be going or which area they want to cover. Moreover, this intensity of the light corresponds to how much the robot should care about covering that specific area. And again, agents have no idea, these robots have no idea where this more important area will emerge. So they are just doing it in a purely collaborative manner. They are just talking with each other and exchanging their information with each other and taking local steps. So that is an example of a distributed setup in which robots are performing some concrete global task. The second picture shows a swarm intelligence. Again, these are not lights, these are actually drones. And these drones are these are hundreds of drones, and they are performing some sort of a swarm intelligence and making some nicer shapes, and they are doing it in a distributed manner. In the third figure over here, we have another task, which is the formation control task. Again, the objective here is that there are a bunch of robots, and these robots are assigned a task of making up a certain formation. For instance, it could be a triangular formation, it could be a simple line formation. And why we need them? For example, we might need these robots to form a square formation because they want to make up a landing platform for the drone. And again, they are going to do it in a purely distributed manner, right? Robots don't know where they are lying, what shape they are trying to adopt, but they are just going to talk with each other, and then they are going to assume that is the most appropriate role. And in the final example, we have this target localization example. What is happening here is that we have a particular target, and all robots want to approach towards this target. And again, they don't know a priori where this target lies. They are just talking with each other, and then depending on their neighbors' information, they're updating their own information, and then they are deciding where they need to move, what should be the next position they should be adopting. So hopefully with these little bit of videos, we can see that these distributed decision setup is an extremely important setup especially in multi-robot systems. Not just in multi-robot systems, but in fact, in all these infrastructure networks, this is an extremely important setting. For instance, in the microgrids, with a lot of this new paradigm of having these prosumer networks where each agent is producing electricity as well as consuming electricity, an important task is to regulate the frequency. So how can they do it? They do it in a purely distributed setting. And similarly, there are other applications in transportation systems, water networks. Not just in engineered systems, there are a lot of applications of this distributed decision making. For instance, in understanding of how our brain works, how these molecules emerge, and how the different animals behave the way they behave. So how can we understand their social behavior? So this all is somehow linked to, at some level, is linked to to this problem of distributed decision making. Okay, good. So now let's create a bigger picture of this distributed decision making in a slightly more concrete manner. We have a bunch of agents. Each agent has some state which belongs to some d-dimensional space, and then each agent has some local objective. Okay, so which means that each agent is going to take its new position so as to minimize this local objective, which is JIX. Okay? And the global objective of the network is some summation of, or some sort of an weighted average of these local objectives. Okay, so the ultimate goal is agents are trying to minimize this global objective while cooperating with each other. So the basic paradigm of distributed decisions making is that how can we go from local rules to global objectives using these cooperations with each other. Okay? So this is the kind of a problem setup in a general distributed optimization problem. So how do we solve it? So in order to solve it, there are two aspects. So firstly is, again, we can imagine, we can see that by solving, we simply mean how should agents update their states. Okay? So the agents are going to update their states. How can we design the dynamics through which the agents are updating their states? Now, in order, to design those dynamics, what an agent has has basically two important pieces. Firstly, its own information, its own state, maybe some of the previous values of its own state, as well as the neighboring state, the states of some of its neighbors. Okay? So now the goal is that how can we design a dynamical rule through which an agent can updates it information while incorporating its own state and its neighbor state. The second aspect is the network structure, which basically decides that who is influencing whom, okay? Which simply decides who are my neighbors. And again, one aspect here is that what are the most appropriate structures? How should we design the most optimal structures? So for today's talk, we are not going to discuss this aspect. We are just going to focus on the dynamical side of things. But in a general distributed solution, these two aspects are very tightly coupled with each other. Okay, so let's focus on this dynamics part over here. Again, what we are in the business of designing these dynamical rules, meaning that I am at state X, my state at time T is Xi. How can I pick out my new state, Xit plus 1? Okay, so in almost every distributed optimization solution, there are two aspects here. There are two considerations here, or there are two parts to this solution. The first part is that agent somehow utilizes its own information and estimates its most appropriate action for the next time step. Okay? And the second step is, or the second component of the solution is that agents not only utilizes its own information, but collects information of its neighbors and somehow performs some sort of an aggregation on that step, and then use this aggregated information to refine its own estimate. So almost every distributed solution follows these two simple schemes. Okay? So there is this aggregation step where, for instance, an agent is simply taking a weighted average of its neighbor state. And again, it is going to use this aggregated data to refine its own estimate. Okay, good. So the takeaway so far is this aggregation step actually realizes the fruits of cooperation, and it is the key step here. So the success of a distributed optimization solution precisely depends on how we are going to aggregate our neighbors' information. Okay? So if that step is not done properly, then we cannot do the distributed optimization in a proper manner. So that is the simple takeaway so far. Okay, since this is such an important step, so what happens if there appears some adversary in the network? And what is an adversary? An adversary is something which is not adhering to the normal state update laws. They can just try to, or maybe they have an objective that all the normal agents must not achieve their global objective. Okay? They must, the system should not converge to the point where it should be converging. Now, whenever there is an adversary that appears in the neighborhood of a normal agent, then it can affect the aggregation step. Okay? And the real issue over here is that a node does not know who is the adversarial neighbor in my neighborhood. So that's why this becomes such a crucial task, that a normal agent is completely oblivious of the identity of an adversary if it exists in its neighborhood. Okay? And if a normal agent continues to incorporate this corrupted information in its aggregation step, that it can lead to normal agents not achieving their objective. So for instance, let me show you a simple simulation here. Here we are using, again, giving an example of a target localization steps. These 6 agents, which are circled red, they are the adversary agents. And again, they are just not changing their positions at all. They are just static. And we can see that if we are implementing a standard distributed optimization solution, that all normal robots, which should be actually going towards this blue star, which is their target state, but they are not able to do so because of these adversarial agents. Okay? And the main reason is that these adversarial agents are causing problems in the aggregation step. And as a result, these normal agents are not able to reach to their target state. Okay? So what is the conclusion, or what's the important message here is that if we want to have a fruitful distributed optimization solution, we need to design this resilient aggregation rules. Okay? And by resilient aggregation rules, I simply mean the rules in which neighbors are going to aggregate the data, and the data should be aggregated in such a way that the effects of the adversarial neighbors, they are siphoned out. Okay, so again, there are different considerations now. There are different challenges and problems in order to design resilient aggregations. Some of these challenges are that what does it really mean to have a resilient aggregate solution? Meaning, what are we actually trying to achieve? So right now, I've been constantly saying that agents should aggregate its normal agents data so that the effects of the adversarial neighbors are siphoned out. What does it mean? Where do we want our aggregated solution to lie? Maybe we want our aggregated solution to lie in the convex hull of the normal neighbors. Does that mean that if we can guarantee that, is it the right definition of the accuracy? The second challenge is the resilience. So by resilience, I simply mean that when is it possible? So whatever the notion of accuracy we define for resilient aggregation, when is it possible? For instance, if the number of adversaries, what is the maximum number of adversaries which are even if they are present in my neighborhood, I can still achieve resilient aggregation. Okay, what is that number? What are those resilience bounds? And they are not very easy to find in general settings. Okay, once we define the accuracy and then we define these resilience bounds, then how can we actually achieve those resilience bounds? So what are the real aggregation rules? Should we compute the average? Should we compute the median? Should we compute the coordinate-wise median? What are the right aggregation rules? Okay. And secondly, another important consideration is that these things become really difficult and challenging when we go in the higher dimensions. By that, I mean when the state vector of each agent is in a d-dimensional space, meaning it's a vector, then these problems become even more challenging. So these are the four things that we are going to look now. And if the time permits, I would like to talk very briefly about another very exciting direction, which is this new problem of accuracy versus resilience. It's still open and there is a lot of room to work in this direction over here. Okay. Good. So now, in order to answer these questions or in order to look at these issues, we are going to look at two different flavors of resilient optimization. The first problem is resilient distributed consensus, and the second problem we will look at is resilient distributed diffusion. Okay, so we'll start with this first resilient distributed consensus problem. And again, it's a canonical problem. It's the most simplistic resilient distributed optimization problem. What's the setup here? The setup here is that we have a network of agents. Each agent has a state in a d-dimensional space, and we want agents are exchanging their states in different iterations. And the ultimate goal is that all agents should converge at a common point. Please note that we don't know a priori what this common point is. Agents are somehow going to decide, and they are going to converge at this common point. Okay? So that's why asymptotically, all the normal nodes should converge at some common point X. Okay. Now there are very nice and elegant solutions for that. For instance, if we are able to achieve consensus, the first figure shows that. But if there are some adversarial agents, such as these red agents in the second figure, we can see that we are not able to, the blue agents, which are the normal agents, they are not able to achieve consensus. Okay? Although they are implementing exactly the same consensus state update rule, which is being implemented in the first equation. So again, the adversaries are causing the problem. So let's kind of more concretely define what are the requirements for resilient consensus. So basically there are two requirements. The first requirement is that all the normal agents should the first requirement is a safety condition, which is that all normal agents should remain inside the convex hull of the initial states of normal neighbors at all time. Okay? So for instance, if in this figure over here, these blue nodes corresponds to the initial points of these normal agents, then agents should update their states so that they always remain inside this blue region, which is the convex hull of their initial states. Okay? So that is the safety condition. What's the second condition? The second condition is the agreement condition, which is that all normal agents should eventually converge at one common point, which should lie somewhere in this convex hull. So as long as these two conditions are satisfied, we declare that we have achieved resilience consensus. Okay, good.
Waseem?
Yes.
On the previous slide, so you said we should always lie in the convex hull of these blue nodes. So this is one possible safety condition. Is there any other possible safety condition
Okay.
इस तरह की? Yeah.
I think that's a good question, but in every literature so far, this is the safety condition that people have looked at. And again, we and I think it makes sense.
So my question is, why does it make sense? Yeah.
I think it makes sense in the sense that sometimes these initial conditions corresponds to the extreme conditions of an agent that we don't want to violate. Okay? So for instance, these are, so at any point in time, we don't want our agent to adopt a state which is outside of these initial conditions because they kind of correspond to the extreme state. So I think this is one of the possible interpretations.
Okay, good. Okay.
Okay, good. So let's look at the solution of this resilient consensus. First, let's look at the solution with no adversaries at all. Okay. So if there is no adversaries, the solution is very simple. In each iteration, a normal agent should simply compute an average of its neighbor state, okay, or maybe a convex combination of its neighbor state. A very simple solution. And we know that if the graph is connected, as long as the graph is connected, this simple solution is always going to work. That's great. But what if there are some adversaries that appear in the network? Okay. So the solution that is given to us, or that we know is going to work, is shown in this second equation here. And you see that this solution is exactly same as the first solution, or the solution with no adversaries, with a slight difference. And I hope, can anyone spot the difference? The difference is here, right? So instead of considering all my neighbors, now we are just going to consider a subset of my neighbors. Each normal node is going to consider only a subset of neighbors, meaning it's going to compute a weighted average of only a subset of its neighbors. And that subset is typically what we call as the truncated neighborhood. Okay. So that is, again, that was one of the that should be one of the takeaways of this presentation, that and we will talk about it in more detail, that one approach to achieving resilient aggregation is to obtain a truncated neighborhood and then perform this aggregation rule, average or whatever median on that truncated neighborhood. Now the challenge is that how can we compute this truncated neighborhood, right? So a simple solution over here is, which we know works, is that a node simply collects the values of all of its neighbors. So xik is the value of the node. It's the state value of the node itself, and the blues are the neighbor's values. Then it simply sort these values. Okay. And in the third step,
just a stupid question. So why not just take the subset of good neighbors and just ignore the bad neighbors?
Very good question. So that's why I have been saying this constantly, that we don't know who's the good neighbor and the bad neighbor. Okay. So a node is completely oblivious of the identities of its bad neighbor. So if we know who is the good neighbor and bad neighbor, I mean, we don't need to do anything. We can just go home, right? So that is the real question. That is the real challenge, that we don't know who is the bad neighbor. We are simply getting the values. Okay, so now the thing is that we get the values, then we sort them, and then we remove f largest and f smallest values from my neighbors, from these sorted values. Okay, so we know that what is the value of f. So f is kind of an upper bound on the number of adversaries that can appear in my neighborhood. Okay? So we assume that at most f adversaries can appear in the neighborhood of a normal agent. Again, you can question me that this might not be the most realistic assumptions in all practical scenarios, and that's true. But for this particular case over here, we make this assumption, and it is not entirely impractical. Okay. So anyway, so we remove the f largest values, we remove f smallest values. Whatever remains is our truncated neighborhood. Okay. So now I'm going to simply compute a weighted average, or simply an average of the nodes values in this truncated neighborhood. And there is this beautiful result which says that as long as certain robustness conditions of network, and if the network graph satisfies certain robustness conditions, then this scheme, this truncated neighborhood scheme, always going to work, meaning that we are always going to guarantee resilient consensus. Again, it's a beautiful result. Now, the thing is that these robustness conditions, these are, I'm not going to talk about them here because they they get pretty messy sometimes. Okay? But the main point is that if we are able to compute truncated neighborhood, then we are able to guarantee in a certain way, in some way, that resilient consensus is guaranteed. Okay, so again, this is one of the takeaway message, that using truncated neighborhood has been a very effective approach for resilient aggregation. And again, what is the goal here? The goal here is to prevent adversarial neighbors from corrupting the aggregation step. Okay? And again, the challenge here is, as Dr. Mudassir asked, that we don't know who is the good neighbor and who is the bad neighbor. So what was the philosophy, what was the intuition behind the previous slide, or this idea of truncated neighborhood, is that if I'm a normal node, then the values of my neighbors which lie closer to me are going to be correct, and the values that are going to be too far away from me, perhaps they are going to be the values of the adversaries. So that was the basic idea. So that's why we truncate the values that lies at the extreme, okay, that are too far away from the node's own value. So that is one way of computing the truncated neighborhood. So that is one of the things. So again, it seems a nice approach, but there are certain things that we need to take care. So first challenge here is how many values should I truncate? Okay? Then which values to truncate? Okay? So for instance, as I mentioned, that here we can compute the smallest values, the ones that are farthest away from me. Now this notion of farthest would involve some distance. And when we are in a high dimensional space, this notion of Euclidean distance might not work here. So we need somehow to develop more sophisticated ways of computing these distances, or finding out what do we mean by saying that what the values that lies farthest for me. And again, as I mentioned, that there are going to be problems in high dimensions. Okay. But nevertheless, this is a very useful approach. So now let's change our gears to the resilient consensus in higher dimensions. So far, the case I was looking at was for the scalar case. Probably I didn't mention that, but each node state was a scalar value over there. And that's why there was no issue of sorting here. Okay, so since it is a scalar, we can easily sort the values of my neighbors. But when we have, when the state of a node becomes a vector, then how can we achieve resilient consensus? So one simple approach could be that simply implement resilient consensus in each direction, in each coordinate separately, and then we can be done with that. Okay? So is this a good approach? Let's see. So in this figure, we are shown a two-dimensional state, right? Each node has a two-dimensional state, X and Y. So if we run resilient consensus in X direction, we are guaranteed to converge between the minimum and the maximum X values, right? Similarly, if we run scalar consensus in Y direction, we are guaranteed to converge between Y min 0 and Y max 0. Which means what? Which means that we are guaranteed to converge somewhere in this yellow box over here, right? But what was the requirement for our safety condition for resilient vector consensus? That we should always be converging inside the convex hull of these normal nodes. But here we can see that there are some points in the yellow region which do not lie in this blue region. So this approach of implementing, let's say if we are in a D, if the state vector is D-dimensional, then this approach of dividing the D-dimensional state into D one-dimensional states and running D instances of scalar consensus is not going to work. Okay? So we need to do something more sophisticated here. So recently, an algorithm, a very simple algorithm for resilient vector consensus was proposed by Park and Hutchinson in this paper. And the idea is very simple. The simple idea is that in each iteration T, a normal node I finds a point SIT that lies in its normal neighbor state. Okay, so simply I'm talking about node I, and I want to compute my new position. Let's say I'm a robot I, and I want to compute my new position. How would I compute it? I would simply compute a point that is guaranteed to lie in the convex hull of my normal neighbors. Once I'm able to do that, I can simply move towards that point. Okay, that's a very simple approach which is guaranteed to work. But as probably you would have noticed now, that this seems to be a simple approach, but the biggest challenge over here is that how can we compute this point SIT, right? Because this SIT should lie in the normal should be lying inside the convex hull of normal nodes, but I don't know who are my normal neighbors. So how can I compute that point, right? So that is leads to a new problem, which is that I have a bunch of points, okay, given a bunch of points, some of which are normal and some of which are adversarial. How can we compute a point that is guaranteed to lie in the convex hull of normal points? And such a point is called as a safe point. Okay? So let's define that safe point. Again, a safe point is that given a set of endpoints in RD, of which any of the F points can be adversarial. And again, please note why we want and this anything to be. I want to emphasize this notion of any of the F points because we don't know who those F points could be. They could be anyone. So we want a point that is guaranteed to lie in the convex hull of normal nodes, given that any of F of these endpoints can be adversarial. Okay, and then such a point is called as a safe point.
Um, Waseem, can you hear me? Uh, Ubaid, Farooq, can you guys hear me? Waseem, can you hear me? Waseem, your mic is off, I think. Waseem, your mic is off, I think. Waseem, can you hear me? Your mic is off. Your mic is off. Oh, okay. Just give me a second. Yeah. Okay. Try unmuting yourself. Can you unmute? Yeah.
Okay, yes, I can hear now.
Okay. Sorry. Go ahead.
No problem. Okay, so let me share my screen again and we'll continue from where we left. Okay. Okay, good. So I was just saying that these yellow points is basically the set of points which is guaranteed to lie in the convex hull of normal points. And how to see this, we have just simple simulation that shows it. So in this simple simulation, what is happening is that we are picking any of the 5 nodes, okay, and any of the 5 nodes, normal nodes, and we draw the convex hull, which is this blue region, and you can see that this yellow region is always lying inside this blue region, no matter which of the 5 points we are picking as normal nodes. So what does that mean? What this implies that every point in this yellow region is going to be a safe point, meaning it is always going to lie in the convex hull of normal region, convex hull of normal points. Okay? So this is what we are trying to look for. Okay. Now the question is, when can we guarantee the existence of this F safe point? Okay. So if the number of F is too large, then this F safe point might not exist at all. So first question is, what are the conditions on F which can guarantee that this F safe point exists? And secondly, how can we actually find this F safe point? Good. So one such solution is using this idea of Tverberg partitions. Again, the idea is very simple, that given these set of points, we partition it into some subsets, okay, and then we compute the convex hull of every set in that partition. For instance, here we have 6 points. We divided it into 2 subsets, each consisting of 3 nodes. We compute their convex hull. Then these partitions or these subsets should be such that their convex hulls must intersect. Okay, so for instance, in this case, we can see that the convex hull of these 2 subsets are intersecting, which is this brown, which is this gray region. Okay, so let S be the number of subsets in the partition and F be the number of adversary nodes. Now, interesting thing is that if the number of partitions is 1 more than the number of adversaries, then what would happen is that there will be 1 subset in the partition which would only be consisting of normal nodes, right? Because there is 1 more partition, right? So which means that if all the convex hulls of all the partitions, all the subsets in the partitions are intersecting, then that intersection point, that intersection region necessarily contains a point that lies in the convex hull of all normal nodes, right? And again, I can repeat that because that intersection region would lie in the convexal of a subset consisting of only normal nodes, which mean this intersection region consists of points that lie in the convexal of all normal nodes. That's great. So if somehow we can find this intersection region, we are done. We have figured out, or we have found a point that is guaranteed to lie in the convexal of normal nodes. So now the question is, when can we guarantee the existence of this intersection region? Okay. And there is this beautiful theorem by Tverberg, proven in 1960s, which states that if D is the dimension of state, Ni is the total number of nodes, and Fi is the number of adversarial agents in the node, then we can always find this non-empty intersection as long as this condition is satisfied. Okay? So that is an amazing thing, because if the number of adversaries, now we have a bound which says that if the number of adversaries is less than this particular bound, then we can always find a point that is guaranteed to lie in the convexal of normal nodes, and which would guarantee our resilient consensus. That's great. But in order to finding this point is not an easy job. In fact, the actual condition that we need in order to find such a point is actually more conserved or more restrictive than the theoretically best possible bound. And this bound is basically given in this second expression over here. Okay? But we still have a bound. Okay? We still have a condition which would guarantee that if the number of adversaries are lesser than this thing, then we are always going to converge. We are always going to find a point in the convexal, which would ultimately lead us to showing that we will always converge and we will always achieve resilient consensus. Okay? And these results were actually shown to be true when as long as the dimension of the state was lesser than 8. So we asked these questions. So first of all, this condition was a sufficient condition. So the first question we asked was that, is it a necessary condition also? Secondly, can we actually improve this practical resilience bound? Okay? And the third is, these results were valid as long as the dimension of state was lesser than 8. Can these results be taken or remain valid when the dimension is greater than 8? So these three questions were something that we asked, and we answered them. We answered them using this very nice idea of center point. And again, let me just describe the center point. Center point is, again, let's look at this figure. It might be easier to see it over here. The center point is that given a set of points, let's say there are 6 points here, and these two-dimensional state, center point is a point such that if we draw any line passing through this point, then this line should divide my region into 2 regions, such that each of these regions should contain n of points. How many points? Precisely, each of these regions must contain at least n by d plus 1 points. Okay? So you can see that here we have 6 points, d is 2. So if we draw any line through this star, which is the center point, then we are getting 2 regions, each of which is containing at least 2 points. Okay? So that is what is called as the center point in 2 dimensions. And we can extend this definition to higher dimensions, which in that case would be that any hyperplane that passes through this point should divide the region, in d-dimensional region, into 2 subregions, each of which must contain at least n by d plus 1 points. Now, some facts regarding center point, that it is basically generalization of median in higher dimensions. So what a median does in 1 dimension, it simply divides our 1-dimensional line into 2 parts, right? And in each part into 1-dimensional, it simply divides the 1-dimensional points into 2 parts, and each part contains n by 2 points. So the idea is basically similar here, but in higher dimensions. And we know center point always exists, and center point is not unique. Okay, good. So for instance, every point in this yellow region is indeed a center point. Again, satisfying the center point, meaning if we draw any line to that point, it would divide the region into 2 almost equal regions. Okay, here comes a one of the main results that we proved, that for a set of n points in RD, as long as f is equal to n by d plus 1 minus 1, then the region of f safe points is exactly same as the center point region. And again, recall what was the safe point region? The safe point region was the one which was guaranteed which consisted of the points that were guaranteed to lie in the convex hull of normal nodes, no matter which of the given points are adversaries. Okay? But those points, those safe points, would always be lying in the convex hull of normal nodes. So using this center point, we have a complete characterization of the safe region. Okay? Previously, we only had a partial kind of a characterization. By that, I mean that this idea of Tverberg partition, which was giving us this intersection region, right? This intersection region, that and every point in that intersection region was an F-safe point. But again, you can see here that this intersection region or this Tverberg region is basically a subset of our center point region. Okay, but so which means again that the center point based characterization of F-safe points is a much better and a complete characterization. Okay, so in short, what we have found out exactly the conditions under which we can find a safe point, and these conditions are not only sufficient but also necessary one. Okay? As I'm mentioning here, that the condition that we found previously was a sufficient condition, but here we are showing that it is not just a sufficient condition but necessary condition, meaning that if F is violating this bound, then the adversaries can actually take us arbitrarily far away from the convex hull. Okay? Good. So now with this complete characterization of F-safe points using center point, we can present our results, which is that in 2 and 3 dimensions, as long as the number of adversaries is lesser than this particular bound, the first bound shown over here, then we are guaranteed to converge, we are guaranteed to achieve resilient consensus. Okay. Now, if the state dimension becomes higher than 3, then the number of adversaries, if the number of adversaries is omega of n by d square, r can be any positive integer, so let's pick r equals to 2. So if n by d square, then again we are going to make sure that F-safe point exists, and we can find a point in that F-safe region, and we are going to converge. An important thing to observe here is that these bounds are better than the ones provided by the Tverberg based conditions, right? So which means the center point based characterization provides us more tighter practical bounds. Okay? And and as a result, we are also able to improve the resilience of our algorithms to a certain extent. Okay. Now I have also shown some. Now finding this center point is not as easy. It's still challenging. In 2 and 3 dimensions, we can easily do that. In higher dimensions, there are algorithms which can provide a center point. Okay, good. So the final conclusion regarding this resilient consensus idea is that if we are in 2 and 3 dimensions, then center point achieves the theoretical bound. Okay, so meaning that we can achieve the resilience bound if, as long as the number of adversaries is lesser than this number shown here, we are always going to guarantee that we converge, and we are always going to achieve resilient consensus. In the case of higher dimensions, center point provides us more resilience as compared to the Tverberg based condition. Again, so that is again one of the important message here, that center point based aggregation, resilient aggregation, is better than the previously known resilient aggregation. Good. So here, let me quickly show here some simulation results. So let's say we have a total of 45 robots in a plane. 5 of them are adversarial, and blue nodes corresponds to the normal nodes, red corresponds to the adversarial agents, and yellow robots are the ones that are satisfying the center point based conditions, but they are violating the Tverberg based condition. Okay, so if we use the Tverberg based resilient consensus algorithm, we are not going to converge. And this is indeed the case, which is shown by this second plot over here. You can see consensus is not happening, right? But here in the, if we use the center point based aggregation rule, we are indeed achieving resilient consensus. Okay? And that is again an important improvement, that previously we were not able to converge, but now we are able to converge while improving the practical resilience. So let me kind of summarize this idea of resilient consensus is that somehow we need to aggregate information, our neighbors' values. And this aggregation must satisfy one condition, which is that the result of aggregation must lie in the convex hull of normal nodes. We don't know who are my normal neighbors. Okay, so now somehow we characterize this idea, this set of points which are guaranteed to lie in the convex hull of normal neighbors, and we call them as F-safe region. Okay? Now we can compute this some points in that F-safe region using Tverberg-based partition, which people have done previously, or using this center points-based aggregation rule, which we proposed. And we here showed that center points-based aggregation is indeed better than the Tverberg-based partition. Okay? So this concludes kind of the first aspect, which is the resilient consensus. So Mudassir, I don't know how much more time do I have. Should I go through this resilient diffusion?
I think you should just conclude in next couple of minutes or so. I
Sure.
think
So let me,
yeah, we're
so
running out of
basically,
time.
sure. So basically I have some more slides which again discuss another flavor of distributed optimization, which is slightly more advanced as compared to the, let me quickly show this problem only. Yeah, so which is more advanced as compared to the resilient consensus. Here we are going to use any general local cost function. The only condition is it should be strongly convex. And again, there are some solutions. And what we showed, okay, let me show you the final result, is that if we use the center point based aggregation again in the solution, there are two steps. The firstly, an agent estimates using its own values. And the second step is that it aggregates its neighbor state. So we propose that in the aggregation step, use center point based aggregation as we use in the case of resilient consensus. And it turns out that the center points based aggregation provided much better results as compared to previously known results. So for instance, here we have three different simulations. One aggregation rules coordinate-wise median, that in each coordinate we are taking the median. In the second case, we have a geometric median. In the third case, we have a center points-based rule. And it can be seen again that using center points-based aggregation, we are able to achieve our global objective, which is the target localization. Okay? So I can share the slides, and those of you who are interested in seeing the theory behind this distributed diffusion and this idea of center points in distributed diffusion, please feel free to do so. So let me conclude. So conclusion is that, as I've been saying throughout this talk, this resilient distributed optimization has an important step, aggregation of neighbors. There can be two approaches. The first is somehow truncate the neighbors. Okay? Somehow compute each node, normal node, should compute a subset of its neighbors, which it believes are the right ones. Now, computing that might not be the straightforward task, but there are ways of doing that. So once we do that, there are ways to show that using this truncated neighbor, using aggregation rules on this truncated neighbors gives us good result. Another approach is the center point based aggregation, again, in which we simply compute a center point of the given set of points. And we covered this resilient distributed consensus part. We couldn't cover how these two approaches are applied in the case of resilient distributed diffusion. Maybe some other time we can discuss that. And finally, the center points based aggregation has some advantages, which is that they give us very nice analytical results. Sometimes these results are difficult to obtain when we are using this idea of truncated neighbors. Okay? And again, in higher dimensions, it makes a lot of sense. And finally, I wanted to talk a little bit about this resilience accuracy trade-off, but again, in the interest of time, I'm just going to skip it. And I hope, again, please take away the two messages here. So the two messages are that in order to do resilient aggregation, you can either do truncation or either you can do some sort of center point based, which is basically the generalization of this idea of median in scalar states in the higher dimension states. So with this, I conclude, and I would be happy to answer any of your questions.
Great, thank you so much, Dr. Waseem. I have unmuted everyone, so you can unmute yourself and ask any questions you may have for Dr. Waseem. So please feel free. I can probably start the first question. Dr. Waseem, many of us would be interested in knowing the application of this this resilient consensus work in the area of machine learning. So I know that you recently had a paper published in NeurIPS of this year which also revolves around the idea of resilient consensus, as far as I know. So maybe you can just give us a review of application, how this can be applied to machine learning tasks.
Again, I'm also kind of new to this machine learning area. So, okay, that's that. With that disclaimer, let me say one thing. What I have seen that uh, uh, every distributed learning or distributed optimization problem involves this step, the step where we somehow have to combine information from our neighbors, right? And then using that neighbor aggregate and then aggregate it and then use that aggregated information to further refine my own estimate. Okay, so whenever there is some sort of aggregation going on, we need a way to siphon out or get rid of the bad effects of these corrupted neighbors that might be present in my neighborhood. So these ideas can be applied over there. Actually, the second application that I had over here was related to this distributed learning. Uh, Let me quickly show. So basically, if you look at this solution over here, this is simply a solution to a generalized distributed learning problem over here. We are trying to learn the parameters W naught, okay? And how we learn it, we simply each normal agent probes the system using some sequence, input sequence, and see that how the model or how the system responds to excitation, obtain these output sequence. So DK's IS are output sequence, UK's IS are my input sequences. And then from that information, we somehow try to obtain these parameters. And this is the distributed learning algorithm that does it basically. And and again, you can see there are two steps. The first step is the adaptation step, which simply means that agent K is somehow estimating its own state. And in the second step, it is combining its neighbor's data to refine its own estimate. This first, in the second term, in the first equation, is nothing but basically an approximation of the gradient descent of my local cost function. So this is learning. This is precisely what is learning going on. And you can see that we can easily show that if there are some bad neighbors over here, this learning is not going to work. We could go arbitrarily far away from our true target. Okay. So how can we do that? If we can utilize this center point based aggregation over here, we can, we can actually converge. This is what we, the idea of this truncated neighborhood to achieve that. So, I think that, so in summary, I have said it in a much longer way, but in summary, wherever we need to somehow combine information from our neighbors, may it be a learning application, may it be an optimization application, these ideas of truncation and these ideas of center point based aggregation, they could come handy.
I see. Nice, great. Any questions, people?
Sir, I have a question.
Okay, Nimra.
Sir, can we map this minimizing an objective function to minimizing an error when we do training in machine learning? And if we are not given with some neighboring nodes, can we assume that the data set we have and there is no neighboring information? So can we say something here? There are some instances which are basically maximizing the error, and we can just identify those instances and we can label them as, adversaries and something. So I just want to map this to machine learning. So can we do that?
So Nimra, probably,
okay. Just to I don't know, add my part to this question. So where does this neighborhood come from? In machine learning, I have data, and it's probably distributed over multiple machines, and I'm trying to learn from these distributed machines using distributed gradient learning, right? Where does this neighborhood come from? And yeah, I guess.
Again, probably, Dr. Mudassir, you are in probably a better position to answer this. Again, my perspective of learning is pretty limited here. But let me see what we are doing here. So basically, we are receiving data from all these different machines. right? So isn't this give us an idea of, this realizes this notion of neighborhood? Some of these machines could be providing us a faulty information or incorrect information, and somehow we want to get rid of the effects of these faulty information. So that could be that could be a kind of a setting where we have neighbors, and some of which might be corrupted, and we want to siphon out uh, their effect. So again, I don't know what more to say regarding this this learning setup that Nimra has mentioned.
You're perfectly right. So just to probably add my perspective to it. So the thing is, हम जब neighborhood की बात करते हैं, as such, it's nothing more than मेरे पास I'm a centralized node और मेरे पास 4 computers हैं जिसके ऊपर मैं learning कर सकता हूँ. I'm just using their resources. तो मेरी neighborhood is just those 4 nodes, and they're locally learning from the data that I gave them. And after learning, they tell me whatever they have learned. Okay, well, let's say one of those computers is bad or got bad examples or something, और उसने कुछ bad learn किया है जो मैं नहीं चाहता था कि मेरा objective उस तरफ जाए. तो I somehow need to aggregate this information to find out कि मुझे actually कहाँ पे जाना है. लेकिन जिस topic पे डॉक्टर वसीम ने अभी talk किया, उसमें the main part was कि we don't really care कि which one of them is bad. हमारा aggregation step actually somehow removes the bad guy anyway, right? हम कुछ ऐसा कहते नहीं है कि this is a bad guy, इसकी value बहुत दूर आ रही है मेरे objective function से, so he might be bad. हम ऐसा कुछ नहीं कहते, we just ignore this fact. लेकिन हमारा जो aggregation का step है वो ही इतना sophisticated है कि it automatically compensates the effects of a bad guy.
Yes, and I just want to say one more thing, that please note that this is a different problem than detection. Okay, probably in detection, the goal is that we want to identify who is my bad neighbor. Okay, that could be one way of getting rid of the effects of bad neighbors, that we somehow first solve the detection problem, and then we know that these are the bad guys, and then we are never going to consider them again. But in many settings, especially in the network controls, we really actually don't have any information about the identities of my neighboring nodes. Okay? So in that case, we cannot figure out that, or we cannot assign a particular label to one of my neighbors. In that case, this setup makes more sense. And also the requirement, there are certain conditions under which detection problem could be solved, and those conditions sometimes are not satisfied by our network. So just wanted to highlight that we are talking about two different problems: detection or this aggregation problem without detecting nodes.
Thank you, sir.
Welcome.
All right.
Probably I haven't answered your question, Nimra, but still, thank you.
All right. Anyone else with a question?
Yes, I have a question.
Sure, go ahead.
Okay, so I have seen the simulation. So the adversaries are like they are not moving, or I think in this study they are not collaborating in a way like the other safe nodes are collaborating. So there's a in a way there's can be a setting we can study, like the adversarial nodes are collaborating, or they are not stationary, they can move to make difficult for the safe nodes to reach the objectives, like to make it more difficult version of this problem. So this it can be possible, like
right. So Amar, very yes, it's an amazing question, excellent question actually. So I would like to point out that this setting, or whenever in this whole talk, whenever I mentioned adversary, this is precisely what I meant. So an adversary is a node which can send arbitrary values to its different nodes. So let's say if I'm a bad guy, if I'm an adversary, and I have 3 neighbors, that I can send arbitrary value to my first neighbor, which could be different from the value that I'm sending to my second neighbor, and which could be different from the value that I'm sending to my third neighbor. So this kind of adversary is called as a Byzantine model. Okay? And they are kind of the guarantees that we are obtaining or that we have obtained, they remain true because these are the guarantees for the worst possible cases. So although in these simulations we show that the adversaries are basically static or crashed agents, but the models that we incorporate, they are fairly general. They are Byzantine adversaries, and they satisfy the criteria that Amal you mentioned. They are pretty smart adversaries. So the bounds that we obtained are the worst case bounds. I hope I answered your question.
So the
Yes,
theoretical
thank
model is actually capable of handling the real adversaries who can
Okay.
collaborate with each other and make really the
Okay,
life
yeah.
of normal nodes tough. But in practice, we don't know. हमारे पास कोई मॉडल नहीं है कि adversarial nodes को क्या करना चाहिए. अगर for example वो दूर जाना शुरू कर दें, तो भी हमारी नोट्स को थोड़ा सा उसका अंदाजा हो जाता है कि वो दूर जा रही हैं. तो द थिंग इज दिस इज एक्चुअली एन ओपन क्वेश्चन, और डॉक्टर वसीम और मैं डिस्कस करते रहते हैं हम इसको कि एडवर्सरी का कोई इस तरह का मॉडल हो जो बहुत सस्पिशियस भी ना हो एंड इट स्टिल अफेक्ट्स इन सम वे. तो इसलिए हमने मेरे ख्याल में सिमुलेशन में डॉक्टर वसीम ने यहाँ पे स्टैशनरी नोट्स यूज किए हुए कि ऐसा कोई मजे का मॉडल है नहीं हमारे पास फॉर एडवर्सरियल नोट्स.
Exactly. Or actually, this is as Dr. Mudassir said, that this is a very good question. क्योंकि देखो हम यहाँ पे हम worst possible case के लिए अपनी bounds दे रहे हैं. And the worst possible case would mean that we are also taking care of the situations which can never happen practically, right? So if we have a more realistic model of adversaries, probably we can do better than these theoretical bounds that we are obtaining. Okay? So this also kind of takes us to another question of this resilience versus accuracy, which I couldn't talk about. But again, this is a very good question, that how can we incorporate the practicality of these adversary models and then leverage this to kind of relax these resilience conditions that that we know as of now.
Thanks.
Great, good question, Amar. Any more question? We probably have time for just one more question.
Ubaid here, sir. I have a question.
Okay, go ahead.
Sir, what is the robot's idea of target? Like, if they already know what the target is, shouldn't they just move to that?
Yes. Okay. Yeah. So, Ubaid, so the robot don't know what the target is. Okay. So target again. So see, let me show you. This is what it is. So basically the target, look, देखो ये second equation जो आपको नजर आ रही है. So we are trying, the target is this W naught model. These are the parameters of some linear model. Okay. So how robots are doing it, they are trying to probe this model by generating some stream of data, which is, let's say, UKI. Okay. And then that stream goes to the model, and then they kind of observe the output sequence, which is this DKI, which is also impacted by the noise. Okay? So this is the information that about the target or about the model or about the parameters that they are trying to approximate, the robots are trying to approximate, robots have. And then they are going to use this UKI, this input sequence data, this output sequence data, which is noisy, and then they are trying to somehow approximate or estimate this actual parameters of the model. So it's not that we know this. If we know what the W naught is, then you are right. I mean, there is nothing to optimize, right? Robot can just go directly over there, but we don't know that W naught directly.
Okay, so this is the only thing that we have control over, right? So यही वो चीज़ है जो हम robots को बता सकते हैं, बाकी सब कुछ उन्हें खुद ही decide करना है.
Yes. So उन्होंने क्या decide करना है? उन्होंने basically ये decide करना है कि what should be their new estimate of the parameter, of those parameters, right? So this is what we mean when we say that it's a dynamically they are updating their state. So I estimate that maybe this is the right at current time my estimate my guess of the actual target is WKI or WI, let's say. Now, how should I further refine it? In the next iteration, मुझे इससे बेहतर estimate को करना है अपने estimate को. How can I do that? I can use my neighbors data. उनके models जो उनका estimates है, उनको मैं somehow utilize करूँगा और मेरे अपना जो current estimate है उसको utilize करूँगा. Does that make sense?
Yes, sir, absolutely. Thank you very much.
Great. So I said it was the last question, but I'm gonna allow one more if there is
Sure,
a
sure.
short question. Well, I guess there isn't. Okay. Awesome. Thank you so much, Dr. Waseem. Everyone, please unmute yourself or thoda sa clap kar dein Dr. Waseem ke liye just to so that would be great. Okay. So we are unmuting in 1, 2, 3. Yay.
Thank you so much, everyone.
Thank you so much, Dr. Waseem. Thank you, everyone, for joining us.
Thank you.
Okay.
Bye.
Bye-bye.